Well, this work was carried out in collaboration with Fernanda Duplancic from San Juan and Diego Garcia Lamba here in Cordoba, and we analyzed the relative population and the properties of galaxies, especially the active ones, in large-scale under-density regions. I led the AstroPH ID in case someone wants to see more detail the work. And in order to do this work, we identify voids in volume limited samples in SLOAM. Here you can see the distribution of redshift and radius. And we obtain spherical voids. This allows us to define the large scale regions in terms of the void-centric distance. We select galaxies in a large scale region called void interior that correspond to the more inner regions in the void with distances more than 0.8 in void radius units. The other under the region we use is the void wall, that are the outer parts of the void and correspond to regions between 0.8 and 1.2 in void radius units. And we also consider galaxies in the field that are far enough from the voids. Here you can see an illustration of galaxies. It's a stacking of different voids, and different colors correspond to galaxies in the different large scale regions. So, taking into account this definition, we select galaxies following these selection criteria and the position relative to the voids, and we obtain the 3 subsamples correspond to the different regions, and you can see the number of galaxies. Clearly, we have very few galaxies in void, but that's enough to perform our analysis. And here you can see the luminosity distributions and the redshift distribution of the different samples. The colors correspond to the different large scale regions. And in the upper panel, you can see that the absolute magnitude distribution is similar for the 3 subsamples. This is important in order to avoid luminosity biases. Then we classified the galaxies following 3 different criteria. The first, the Bpt Diagnostic Diagram, is probably the most useful and the most classical criteria to select active galaxies using the Bpt diagram that use 4 spectroscopic lines. We can select galaxies, star-forming galaxies, composite galaxies, and AGN. We can also use the one diagnostic diagram. This has the advantage of use only 2 lines, and we can classify galaxies as star-forming, strong AGN, weak AGN, and we can also obtain retired and passive galaxies. And the last and different criteria is the wise color diagram. This is different because it uses photometric data in the infrared region. In the case of BPT-1, we use spectroscopic data in the optical region. And with wise criteria, we obtain star-forming, AGN, and passive galaxies. And the figures show the distribution of the galaxy classes in the 3 criteria, and we in the x-axis you can, if you can read, there are the names of the different galaxy classes. The colors correspond to the large scale regions. So here we can see that in the field that is the red, we have a population dominated by passive galaxies. You can see in the one and wise galaxies, and in the void, that is what are we interested. that is the red and green colors, we have a population dominated by star forming and also AGN. It's a little bit hard to see in the Ys because we have very few number of AGN, but also we have an important population of AGN with Ys. This is a new result because it's a very well-known behavior of galaxies in void to be star forming, but we didn't know that there was AGN also in voids and in a very important number of that. To see this in more detail, we also analyzed the galaxy fractions of the different galaxy classes as a function to the distance to the void. And we these are only for one and wise galaxies. And in pink lines, for both figures, we can see the fraction of AGN galaxies as a function to the distance. So to the left, we obtain we show the void regions in both figures. And you can note that the fraction of galaxies in void and worlds increase in both criteria. And on the other hand, in green lines, we show the star forming galaxy fractions, and in this case they also we also obtain an increment, and for the passive galaxies in blue lines we obtain a decrease of these galaxies of these fractions in void regions. For one galaxies we also analyze the relative fraction of strong AGN to weak AGN, that is this upper panel, and we can note a notable increment of this fraction in void regions, and in the upper small panel we see the relative fraction of AGN to retired galaxies in the pink line. Here we can also note an increment of the fraction of AGN relative to retired galaxies, and the green line shows the fraction of star-forming galaxies relative to retired. Here we can note an increment, and this is consistent with previous results. For the one galaxies, we analyze the behavior of the equivalent width of H alpha. This line is related to star formation, but it's also have information about the AGN phenomena in galaxies, and the upper histogram shows the distribution of the equivalent width for star forming galaxies, and the lower panel is for strong AGM. The colors correspond to the large scale region, and for star forming we can thank you. We can note the very similar distributions, but for strong AGN we can see that the values are higher for galaxies in void, especially for void interiors. Examining the mean values of the equivalent width as a function to the distance, we can see in more detail this result. The pink line is for strong AGN, and we can see the notable increment in the fractions in void and walls. For weak AGN in this lower line, we can note a decrease of this fraction, and surprisingly for me, the equivalent width of star-forming galaxies is similar for all the large-scale region, for all distances. And for Bpt AGN, we analyze the behavior of the luminosity of substation 3, and this is a proxy of the AGN activity. So we expect a fine sign difference, and we obtain that for galaxies in void interior, that is the red histograms, we obtain higher values of this luminosity. But the luminosity of oxygen 3 is related with the black hole mass. So in order to avoid these possible biases, ahora sí, okay. Well, let's continue. We use a proxy for black hole mass, and we select samples according to the black hole mass percentiles, and these are the luminosity oxygen 3 distributions for galaxies in void wall in green and in void interior in blue, and the red is for comparison the field. And for all different percentiles of black hole mass, we obtain higher values of this parameter in voids. We analyze also the mean value of the luminosity of oxygen 3 as a function to the distance to the void, and the different color correspond to different percentage of black hole mass. The darkest is for lower mass, and the lighter for the higher mass. In spite of the percentile and in spite of the black hole mass, we obtain higher values for the luminosity of oxygen 3 in void and walls, and this is consistent with an increase of the black hole of the AGN activity in voids. We also analyze the powerful AGN. With one galaxies, we have strong AGN, and to obtain something similar with Bpt, we use this definition. The powerful AGN are those with luminosity of oxygen 3 greater than 10 to the 7, and these are the fraction of this powerful AGN as a function to the distance to the void. Colors are similar than the previous figure, and here we obtain a similar result. Powerful AGN are dominate on void environments. And we also analyze the role of infrared galaxies in the distribution of the luminosity of oxygen 3. And here we show each panel corresponds to different large scale region, void in the lower and field in the upper. And we obtain 4 galaxies that are Bpt and also WISE. They follow the 2 criteria. In yellow, we obtain similar distributions for the 3 regions. And for galaxies that are Bpt and 1 at the same time, we obtain also similar distributions. And if we analyze the void environment, the void interior environment, the lower panel, we obtain similar distribution for the 3 criteria, and we also obtain a remarkable fraction of powerful AGN for the 3 criteria. So in conclusion, the galaxies that are Bpt and WISE at the same time are the most powerful objects in the 3 large-scale environment. And to finish, we analyze the efficiency of AGN. And to do this, we define an accretion rate parameter in this way. And I show you here the mean value of this accretion rate parameter as a function to the distance to the void, and we obtain that, and the color correspond to the same subsamples in the previous slide. The green, the black is for galaxies that are only Bpt, AGN, and the yellow correspond to galaxies that are WISE and Bpt, and green that are 1 and Bpt. And for the three subsamples, we obtain an increment on the accretion rate parameters in void environments. Oh. What happened here? Sorry, I don't know what happened here. So the galaxies that are Bpt and also WISE are the more powerful and more efficient objects in our samples. And to finish, I want to say only two things that are our more important result is that we find an increment of AGN galaxies in void environments, and and these galaxies are the more powerful and efficient galaxies in our samples. So galaxies, AGNs in voids are more powerful and more efficient than galaxies in the field.
Bueno. Okay, we have time for a very brief question.
Very nice talk. Thank you. I would like to know if you can say something about the age of the galaxies. These more AGNs near the voids, and so are younger age. Perdón, edad. ¿Puedes decir algo de la edad? ¿Son más jóvenes? Las que están, las AGN, más AGNs, son más jóvenes. Se formaron después.
I'm not sure about if there are. Yeah. Maybe Fernanda can answer that.
Yes, we need stellar population synthesis, but in principle, the luminosity distribution is similar. So we do not expect important bias, because in the interiors and in void environment and the field, we have the same luminosity distribution. But it is interesting to perform synthesis. Also, yes, but the metallicity of the galaxy is for a function is in voids, we find a function of galaxy. That's why we can with this galaxy.
There aren't conclusive results about metallicity of galaxies in voids, but these galaxies are galaxies that most of them are isolated galaxies, so maybe that can affect the evolution. But there are luminous galaxies also, so I don't know.